In today's lecture, we are going to discuss case 1 related with the one-dimensional steady-state heat transfer from extended surfaces. And case 1 is heat dissipation or heat transfer from a fin of infinitely long length. From one-dimensional steady-state heat transfer from extended surface, we have got governing differential equation for fins. Equation number 4, that is d square t x over dx square minus hp over kc into ts minus t infinity is equal to 0. I can also simplify this equation as d square tx over dx square minus m square ts minus t infinity, where m is called as fin constant, represented by square root of hp over kc, and its unit is per meter. I can also represent equation number 5 in terms of excess temperature. Theta x is equal to Tx minus T infinity and theta s is equal to Ts minus T infinity. So equation 5 can also be rewritten in terms of excess temperatures. D square theta x over dx square minus m square theta s is equal to 0. So equation 4, 5 and 6 are governing differential equation for one-dimensional steady-state heat transfer through a fin. Now solution of this governing differential equation 4, 5 or 6 will give me any unknown temperature Tx along the length of the fin at distance x. Equation 6 is linear homogeneous second order differential equation, and solution of this equation will have two components, that is any unknown temperature theta x will be having one part called as complementary function and another part is called as particular integral. So I can write theta x, which is also written as tx minus t infinity, is equal to c1 e to power mx plus c2 power c2 into e to power minus mx, where c1 and c2 are two unknown constants. If I know the values of these unknown constants c1 and c2, I can find out the temperature Tx at any distance x along the length of the fin. So in order to find out the values of these two unknown constants c1 and c2, we have to consider some boundary conditions, and depending upon the boundary conditions, the values of c1 and c2 will be there and we will get expression for theta x in terms of either known temperatures Ts, T infinity and the fin parameter m. These are some of the formulas to be used in the subsequent discussion. They all are hyperbolic formulae. Sine of hyperbolic mx is equal to e to power mx minus e to power minus mx. Cos of hyperbolic mx is equal to e to power mx plus e to power minus mx over 2. Sine of hyperbolic 0 is equal to 1. Cos of hyperbolic m0, this is actually 0, sorry, and cos of hyperbolic m0 is equal to 1. Similarly, differentiation of sine of hyperbolic mx will give me m into cos of hyperbolic mx, and differentiation of cos of hyperbolic mx will give me m into sine of hyperbolic mx. So let us discuss case 1. It is heat dissipation from a fin of infinitely long length. So let us consider a fin attached to the base surface at temperature Ts of infinitely long length. This represents fin is of infinite length, that is L tends to infinity. The fin is exposed to the surrounding at temperature T infinity. So this temperature T infinity is going to remain constant. So yellow line represents T infinity, and at x equal to 0, that is at the root of the fin, temperature of the fin will be equal to base temperature represented by Ts, and at x equal to infinity, temperature of the fin will be equal to surrounding temperature. So this way the temperature of the fin will vary in the x direction from root to the tip of the fin. Now in order to solve the equation 7 for case 1, we will be requiring some boundary conditions. So boundary condition number 1 will be Tx will be equal to Ts, that is fin temperature at the root will be equal to base temperature at x equal to 0. In terms of excess temperature, I can also write this as, so this I can write it as theta x is equal to theta s at x equal to 0. The second boundary condition, temperature of the fin will be equal to surrounding temperature at x equal to infinity. In terms of excess temperature, I can write it as theta x will be equal to 0 at x equal to infinity. That is at the tip of the fin of infinite length. Now let us put these two boundary conditions into equation number 7 in this equation. So what I will get, so boundary condition 1 and equation 7. If I put x equal to 0 into equation 7 here, theta x, left hand side will be theta x is equal to theta s at x equal to 0, and if I put x equal to 0 here, how it will get changed. So theta x will become theta s c1 into e to power m into 0 plus c2 into e to power minus m into 0, or this will become c1 plus c2, because e to power 0 or e to power minus m0 will be equal to 1. Let's say this is equation number A. Similarly, from boundary condition 2 and equation 7, so theta x is equal to 0, c1 e to power m infinity plus c2 into e to power minus m infinity. Now from the mathematics, from the mathematical relationship, c2 into e to power minus m infinity will become 0. Okay, so from this C1 E2 C1 E2 E to power m infinity will be equal to 0. If this becomes 0, now e to power m infinity can't be 0. So this analogy, this entire analogy will be equal to, the entire left hand side will be equal to 0 only where C1 is equal to 0. So from this discussion, we got the value of C1 as 0. Let us put of C1 into equation A. What I will get? I will get theta s is equal to 0 plus C2, or C2 is equal to theta s. It is nothing but Ts minus T infinity. So this way I could get the values of constant C1 and C2. Now putting the values of constant C1 and C2 into equation 7. What is equation 7? Theta x is equal to, the value of C1 is 0, 0 into e to power mx, plus the value of C2 is theta s into e to power minus mx. So theta x will become theta s into e to power minus mx, or theta x over theta s is nothing but e to power minus mx, and theta x is nothing but excess temperature Tx minus T infinity, and theta s is excess temperature for base temperature Ts minus T infinity. So this is the required temperature distribution for case 1, that is infinitely long fin. I can also write this as cos of hyperbolic mx minus sine of hyperbolic mx. So this formula will be used to get this. This formula will be used to get this. So this is the required temperature distribution for heat transfer or dissipation from a fin of infinite length. Then next is heat transfer rate. Heat transfer rate by this fin of infinitely long length. So what we have assumed that it is assumed that heat transfer from base surface to the root of the fin will take place by conduction and will transfer by convection from the fin surface by convection. This thing we have assumed. So basically, the heat transfer from the root of the fin by conduction will be the heat transfer by fin. So the rate of heat transfer by fin of infinitely long length can be given as minus K into AC into temperature gradient along the length of the fin dx, and this entire temperature gradient will be at x equal to 0. And from where we have got this? From Fourier's law of heat conduction. So if I get the value of this temperature gradient dTx over dx at the root of the fin, I can get the expression for Q fin. So minus K into AC d over dx. From this equation, I can get the value of Tx, which is nothing but T infinity plus Ts minus T infinity e to power minus mx, and this entire term is at x equal to 0. So differentiation of this Tx will give me 0 plus Ts minus T infinity, as it is constant. Differentiation of e to power minus mx will give minus m into e to power minus mx at x equal to 0. Let us take out this minus m outside. It will become k into AC into m, and let us put value of x equal to 0 minus m into 0 into Ts minus T infinity. So simplification will give me Q fin, that is rate of heat transfer from the fin, KAC m Ts minus T infinity. So this is the required expression of heat transfer by fin of infinitely long length when it is attached to the base surface. So this way we can solve for case 1.